So now I want to tell you about the third model of computation, which is the word RAM model. And as I said before, these two models, circuits and Turing machines, are more beloved by complexity theorists. But if you're a person that studies algorithms for a living, you use the quote-unquote standard algorithmic model, which for some odd reason they never really exactly want to tell you in basic textbooks. But it's called the word RAM model. And it's some kind of like model that sort of looks like, C, or modeling like C or assembly language or what have you. So to like literally formally describe it takes a while, which is why it's not as pleasant as Turing machines. But you can basically describe it in an understandable way. So here in the word RAM model, memory is not just bits, but it's divided into words of W bits. So like on your classic x86 chip, think of like W as like 64. Like it operates on like 64-bit chunks. And for size and inputs, you always assume that W is at least log n. Now, the first time you see this, it seems very stressful and weird that like, oh, what? You assume that like the size of your word, like your hardware, actually depends on the length of the input to the machine, like the problem? That sounds weird. But I claim that it's actually not weird. Because first of all, like you do it when you study space complexity. If you say, oh, this algorithm takes order n space, you're kind of implicitly considering the case that like you might need more or less hardware depending on the input size. The main reason you assume it is that when you actually want to like model like normal computation, like our palindromes algorithm, like for I equals 1 to n, check if xi is the same as xn minus I plus 1, n plus 1 minus I. You want to assume that like I is just like, it's like an int data type in C. It's just like one number. And it should somehow cost you like space 1. Like it should be an integer. And like that's the kind of model we want to get into. We don't want to say that like, oh, when I do I equals I plus 1, I is storing a number between 1 and n, so it's really log n bits. So then maybe incrementing a log n bit number costs like log n time. Like that's the kind of like Turing machine annoyances that we're trying to get away from, right? We want to be able to say like, yeah, I equals I plus 1. That's like one basic step, cost 1, done. But that's fine, and that's what we're going to do. And you want to set up a model where this variable I can be stored in like one word. But the typical thing like a variable is doing is like indexing into the input. And if the input is size n, you want to like assume that you can store like a pointer in one word. And that kind of means that your word size should be at least log n. So even though like maybe it seems like weird at first, like one should just accept it and get used to it. I mean, you can just take like every result about the word RAM model as starting out by saying like we assume that W is at least log n. Okay. Okay. And as I said, sort of the point of the model is that it like costs time, 1 by fiat to do like a basic operation on words. And this is basically kind of how they end it, like classical undergrad algorithms textbook, right? They don't even really mention this, but they say like, okay, you can add 2 integers in time 1 because that's like a basic operation. But we can try to be a bit more careful. So here are, actually, to be honest, all the basic operations, like addition and subtraction. These are usually like mod 2 to the w. Okay, you're allowed to do that in time 1. Bitwise and an or and not. Like the bar and the and the tilde and C or whatever. And left shifts and right shifts. But you can just specify any amounts between 1 and w and say left shift this word by that number of bits or right shift it. And one more possibility is multiplication. But let me put a question mark here, because we'll come back to that. Because multiplication is a bit less basic than these ones, so we have to think a little bit about whether we want to allow it. Yep?
Also comparisons?
Yeah, comparisons. So you can, yeah, so for example, I guess one could add like, test if 0 or test if greater than 0. So then a comparison is like a subtraction plus it. But yeah, so comparisons. Other basic ones may be writable in terms of these. Any obvious thing I'm missing? Yeah? Oh, things like cosine or calculations. No. In fact, I'm going to talk about that next class, like more advanced calculations. So in particular, if you want to model real numbers here, you better do it by hand by like storing like the numerator and the denominator and stuff like that. So these are like integer operations. And then, there's instructions that have, kind of, like assembly plus RAM instructions. These all take time 1 as well. You have your like conditional jumps or whatever. It's basically like modeling assembly language. Conditional jumps and indirect memory access, by which I mean, if you're storing like an integer in some word, then like time 1, you can get like say the integer is called I, you can get the ith word and pull it out into whatever, a register in time 1. In fact, I guess it's this property that gives the name RAM to the RAM model. Actually, on this subject, if w is much bigger than log n, I'll talk about that in a second. Like, let's say w is log squared n in your model, then with these indirect memory accesses, like in time 1, you can index into like super polynomially many different memory locations. That's kind of considered tacky, and don't do that, is what they suggest in this model. Actually, generally, when if you're studying algorithms, you probably are caring about like polynomial time algorithms. In fact, you're probably caring about the difference between n squared log n time and n squared time. So like it's considered not cool to use more than polynomial space. In general, you should probably try to stick to like linear space. So for example, we can take the problem of given an array of n numbers, add them up. Okay? This is really like algorithms 101, but just to like make a little commentary about it, you could say, okay, total equals 0 for I equals 1 to n. Total equals total plus ai. Okay, if the input is a, an array of n words. Okay? And so finally, in this model, you have the situation that like everything is as you hoped. It's like order n time, and this is order 1 space. So you need like one word to store like I, and like incrementing I implicitly in this loop takes time 1, and the goto to do the loop takes time 1. This addition, actually we'll come back to the addition in a second. This memory access takes time 1. One thing you may notice, right, is if you're getting really stickler, these words, if they're of w bits, are storing integers between 0 and 2 to the w. So the final sum could actually be n times 2 to the w, which would need, the log of that is like w plus log n bits. So that actually wouldn't fit into one word, w plus log n bits. Although it would fit into 2 words, because we assume that w is at least log n. Okay, so extremely technically, like this addition is not just like adding 2 words together, but you're like secretly implementing total by 2 words and like keeping track of the like carries, because the final total could actually need to fit into 2 words. But like that's a very low-level observation that like people think about once and then never mention again. Okay. Any questions? Yeah.
Since all of one space, then what about like the bits it takes to carry like total? Like, wouldn't you need like more than constant space for the number of bits in total?
No, formally you would allocate, I guess, like one word to store I and maybe 2 words to store total, because total, the actual value of total will end up being at most n times the maximum value in AI, which is like at most n times 2 to the w. So finally, the number of bits needed for total would be like log n plus w, which is less than 2w. So it can fit into 2 words.
So we're really counting the number of words when we say space.
Yeah. Yes, good point. We're counting the number of words when we talk about space. Yeah, excellent. OK. Now, in this model, you don't make any assumptions about w other than it's at least log n. I personally like to also assume that w is order log n, because I find it kind of weird otherwise. I mean, I kind of think it's nice that your integers are going to be numbers between 1 and poly n. It's hard to imagine that you would, I don't know, want to use a different case. You know, in real life, maybe w is 64. And so, yeah, n is going to be some number that's, I don't know, at most 2 to the 64. So, yeah. I think most people kind of vaguely assume that w is proportional to log n, and they mainly work with that. There are like some hardcore algorithmic lovers, people who love algorithms and all the details, that even like study, they like to focus on a model where w could be anything, and you want a running time that does not depend on w. And this, believe it or not, is called the trans-dichotomous RAM model. I mention it partly for a joke, but actually people study it. This means like running times that only depend on n. And they work for like all w. And this is an example, right? Like even if the word sizes here are like square root n, then it's fine. Like, you know, you're adding up square root n bit numbers, and you're storing them in square root n bit words. So it doesn't really depend on w here. But I'll see some examples in a second where it makes a difference. The next detailed commentary I would like to make is, let me get back to this issue, whether or not you allow multiplication. And this would be a basic instruction that, like, in time 1 takes 2 words and gives you the answer to their product, which takes up 2 words. I mean, takes 2 one-word numbers and gives you the 2-word product. And basically, it's up to you whether you want to allow it. You know, if you're going to write a paper where it makes a difference, you can say, I'm allowing myself multiplication. Or you're like, I'm doing it without multiplication, like a champ. So the pros and cons are, for pros, it's kind of realistic. I mean, honestly, like the chips these days, like they have a multiplication instruction, which is very fast. So that might seem fine. And as it turns out, having multiplication is very useful, even for problems that don't seem to have anything to do with arithmetic, as we'll see. I suppose one con is that if you want to be kind of principled about like what basic instructions you're allowing to be time 1, I think a very nice and natural principled thing to do would be to allow any AC0 operation, constant parallel time operation. Kind of reminds you of circuits, seems kind of nice. And all these things like bitwise shift, adding 2 numbers, subtracting 2 numbers, ands and ors, these are all in AC0. And so you could be like, that's very nice. My official model is, and this is sometimes called the AC0 word RAM model or the practical word RAM model. Like, that's my model. But some complexity theorists showed that multiplication is not in AC0. So then you wouldn't be allowed multiplication. But as I said, really, at the end of the day, it's up to you if you want to allow it or not. OK, so to kind of explore the interesting aspects of the word RAM model, I want to come back to the more sophisticated problem we talked about at the beginning, which is sorting. And what's actually kind of amazing is at the end of the day, if you're really into like all the fine-grained aspects of algorithmic theory, the best running time for sorting is an unknown research problem. So we'll get to that. So let's talk about the task of sorting integers. And let's assume for the moment that we're in the model I like, where w is like theta of log n. Okay, so you're sorting log n bit integers. Now let's warm up by assuming that the integers you're sorting, for now, are actually literally log n bits in the sense that they're numbers between 0 and n minus 1. There's a very easy order n times sorting algorithm. If you're given n numbers between 0 and n, does anybody want to suggest it? Yeah?
Split them based on the first bit, 0, 1. Split those based on the second.
Oh, we'll get there. It's even easier than that. It's kind of like if you're sorting 1-bit numbers. It's sort of the analogy. Yeah?
Throw them into like buckets.
Yeah, I think what you're getting at is what I would call counting sort. So what do you do in counting sort? You allocate an array for each, key, between 0 and n. Okay, so that's order n space. Maybe exactly n space. And then you just go through the list, and every time you see a number, you increment the count for that key. So like, count the number of occurrences of each number. That's order n time. And now you know the count for every number, so it's pretty easy to reconstruct the sorted list. I mean, you actually just print out 0 a number of times equal to the number of copies of 0. Then you print out 1 a number of times equal to the number of copies of 1, and so forth. So to get the final sorted list, you would do this. For I equals 0 up to n minus 1. For t equals 0 up to, the count of I. Let me just say print I. Right, and that will print out the sorted list. And this is actually still time order n, because if you think about it, you basically touch each number in the input list like 1 time. So it's proportional to the number of numbers in the list. So that's great. The overall time is order n, which is awesome. It's better than n log n. There's one thing which is not super awesome, though, which is that the space usage here is also order n, theta of n, which is kind of like a semi-frowny face, because you have to allocate like n additional memory. And maybe you're like, OK, space order n is not so bad. My input array is also of size n. But like, imagine you're sorting 3 log n bit numbers. In the same fashion. Well, these numbers range between 0 and n cubed. So if you do the counting sort, you would need to allocate an array of size n cubed. And that's pretty gross, right? Like to use space n cubed to sort some numbers. OK, and these could easily, this could easily be your word size, 3 log n. That's pretty gross. In fact, it's not even clear you could still do this in time order n, right? Because to do this last step, you want to like efficiently skip over the counts that are 0. And if they're like n cubed, I mean, if you just go through them like naively, it would take you n cubed time to print it. So then maybe you like need like an efficient data structure to like remember what the non-zero counts are, and then we get like super crazy. I'm not even sure you could still do it in order n time. So this looks good for like linear time sorting if you're sorting numbers between 0 and n, but maybe you're sorting numbers between 0 and n cubed. But there's building on this, there's like a better solution. And the better idea for sorting, which maybe you've seen before, is called radix sort. And the way radix sort works is the following. First, imagine you take your numbers and you first sort them all just in terms of their least significant bit. And then you do another sort on the second least significant bit, and then another sort and another sort until you're finally doing another sort based on the most significant bit. If you think about it for like 1 minute, if you've never seen it before, if you think about it for 1 minute, that actually correctly sorts the integers. As long as it's maybe a stable sort that doesn't reverse 2 numbers that are tied. OK? So it takes a little thought. And that would take time order n w, because this is how many sorts you would have to do. W, one for each bit in your word, and then for each one, you're sorting 1-bit numbers. So you can definitely do counting sort in like order n time and space order 1. So that's good. Yeah, this requires space order 1, I suppose. But if w is log n, this is like n log n. That's fine, but we're trying to get order n here. But another thing you can do is actually, instead of sorting them like bitwise, you can sort them bytewise. Right? You could sort them by least significant byte, second least significant bytes, and so forth. So doing the bits in groups of n, or 8. And that would mean your counting sort would be sorting numbers between 0 and 256, which is still fine. I mean, that's fine. Counting sort will still be order n time, sorting such numbers. And you'd save factor 8 in the number of overall sorts you had to do. That's good. Of course, you should take that to the next level and sort not just by like chunks of 8 bits, but by some parameter, k bits. So in general, if you use this idea with a radix, as it's called, of k bits, where k is, at most your word size w, then when you're doing your counting sort, you'll be sorting numbers between 0 and 2 to the k, so you'll need this order 2 to the k space. But you'll get time, which is order nw over k. Okay, in particular, now you can take k to literally be like 1 times log n, literally log base 2 of n. And what you can conclude is that radix sort overall sorts n words in order n space, which is fine, and order, sorry, I'm running out of actual space here, n times w over log n time. And that's nice because in the usual setting I prefer, where w is maybe 10 times log n, or it's like order log n, this will be linear time in linear space. Okay, so this gives a very pleasant and basically ideal sorting algorithm, order n space, order n time, for any word size that's at most big O of log n. Any questions about that? Okay, so I want to just read to you, I won't write anything, but I'll read to you some improvements to this. So in the normal model, or what I care about when w is order log n, this is fine. But it's not transdichotomous, right? Because the running time depends on w. So some people might ask, well, if w is log cubed n, then this running time is n times log squared n, which is worse than merge sort. Okay, you can always do merge sort or whatever in n log n time, no matter what w is. So people are like, oh, can you still get order n time if w might be larger than log n? That's the question. So I'll now read to you what is known about this. So in 1974, Van Emdebois invented Van Emdebois priority queues. And using them, you can get n times log w time. And in particular, this is n times log n time, unless w is more than polylog n, which is pretty weird. So that's pretty good. And then Kirkpatrick and Reich in '84 got n times log of w over log n, which means it's always at least as good as radix sort. Okay, then in 1990, Fredman and Willard got a transdichotomous result that just works for any w at all, and it's n times log n over log n. So it's a little bit better than n log n, no matter what w is. And in particular, it heavily uses the multiplication instruction, though. So that's arguably a downside. Then in the 90s, Anderson, Hagerup, Nelson, and Raman invented signature sort, which gives you an order n time whenever w is more than log squared n, which basically covers almost all cases. It doesn't use multiplication, but it's a randomized algorithm. And then Hahn in 2004 gave a transdichotomous result n log n for all w, deterministic, and no multiplication. So almost perfect, except it's n log n. And the last result I'll mention is Hahn and Thorpe from 2002. They got n times root log n for all w, but it's randomized and it uses multiplication. So long story short, we still do not know if you can get order n sorting in the transdichotomous model with or without multiplication or randomization. So there you go. Sorting still an open problem.